All right, so we left off talking about question 18.20, and I said we were going to take a look at this one. So it says, for each of the following compounds, determine the position that is most likely to be the site of an electrophilic aromatic substitution reaction. Remember, we call these EAS, electrophilic aromatic substitution reactions. So in A, I have three groups. I have a strong activator. So the hydroxyl is a strong activator. Then we have the methyl group, which is a weak activator. And then we have the nitro group, and the nitro group is a strong deactivator. It's a strong deactivator. Anyhow, so who's going to win? Well, the strongest activator is always going to win. And so the hydroxyl group is the one that's going to dominate. It's going to be the strongest activator. So it could direct to the para position, but that position already has a substituent. Then we have this ortho position that I'm going to highlight in yellow, and this one that I'm going to highlight in red. Could anybody tell me where would it's most strongly direct to the yellow position or the red position? Could anybody tell me? Exactly. Thanks, Anika. Thanks, Erica. It's to the red position, isn't it? Because we rarely get any kind of substitution at the at a 1-3 in between two substituents that are 1-3 substituted. So we would very rarely get anything there. So there you go. So this is the place where we're going to get our activation. Okay, let's try the next one. We'll go a little faster this time. We've got a nitro group. A nitro group is a strong deactivator. The methoxy group, if you remember, it is a moderate activator. So I'll just circle that in red. We'll put here moderate activator. And then the bromine is a halogen. So it is a deactivator. However, it's a weak deactivator. So we'll put here weak deactivator. Like that. So the strongest one is going to be the methoxy. The methoxy is going to direct to the ortho positions and to the para position. You can clearly see that the para position is blocked by the bromine. It's not going to go to this position because it's too sterically hindered by the nitro and the methoxy. And so it's going to direct to this position right here, ortho to the methoxy, like this. And then the last one, we have two deactivating groups. Right, so I would say that this group, right, we have a carbonyl directly attached from this aldehyde. So this is a moderate deactivator. And then this one here is also a moderate deactivator. So moderate deactivator. So if they're deactivators, they're both going to direct to the meta position. So let me use a different color for this one. I'll say if I put this one in red, okay, this one is going to direct to these meta positions, or these positions that are meta to it, I should say. Okay, I'll circle them in red. Okay, and then the blue one, the aldehyde, is going to direct to these two positions in blue. Now, I didn't give you any way to differentiate between these in terms of activity. They're both moderate deactivators. But there is an answer. Could anybody guess? Is the direction going to be stronger to where I have the little red circles or to where I have the little blue circles? Go with your gut. Yeah, thanks, Erica. You're absolutely right. So what Erica says is it's going to go to where the little red circles are, and you're right. And the reason why is because that position is less sterically hindered. Exactly. So less hindered is all we have to write down for that. So there you go. So every once in a while, I'll teach this, and a student will raise their hand and say, well, what if I have two substituents that are the same in terms of their activity? If that ever happens, I'll always give you something like this where it'll be abundantly clear that sterics will dominate. There you go. And even then, it doesn't come up very often, so don't stress about that, okay? The next one for 18.22b, I'll just ask you guys a quick question, and then I'll put the answer on here. But for this one, do we need a blocking group, yes or no? To put the bromine para to the isopropyl group. Do we? No. Thanks, Erica. Absolutely. No, we do not need a blocking group whatsoever. And so this is just a one-step reaction. We just need bromine and our iron 3 bromide, and we're done. There you go. So no block. If you're like, is that it? That's it. That's all there is. So now what we're going to do is we're going to turn our attention to synthesis strategies. And so I went over this with you earlier today. And so we've covered a lot of different reactions. I'd say, things that are really new to you on here. I tried to hammer this home that this is called a sulfonic acid. Then we talked about the Clemmensen reduction, Clemmensen reaction. We talked about Friedel-Crafts alkylation and Friedel-Crafts acylation. What else? We talked about reduction of a nitro. So this reaction here. And what's cool about these is that, you take some of these reactions and you go from something like a meta director to an ortho director just from one reaction, so that's kind of neat. You see that here as well. Here you have an ortho para director, and here you have a meta director. So kind of neat how you can do those transformations. Here again, well, anyhow, those are two really good examples. Anyhow, so let's move on from there. And let's say that on a quiz, I said, what's the best strategy to make this molecule? Which group should I put on first? Should I put the bromine in first, or should I put the nitro in first? Well, let's think about this. The bromine is an ortho para director, and the nitro is a meta director. Could anybody answer? I guess the answer is on here. So we'd have to put the nitro in first, because the nitro is going to direct the bromine to that position. Whereas the bromine, if you were to put the bromine in first, the bromine would direct here and here, right? So it's not, and here, okay? So it's not going to direct to the meta position. So that means you would have to install this first, okay? So we'll put here added first, okay? The nitro has to be added first. Anyhow, that's the worst note making I've ever done, but you get the idea. So we'll just put here added first, like that. So that's kind of the strategy. And as I was trying to tell you before, what's cool about some of these transformations is that you take ortho para directors, like, an alkyl group, and then you turn it into a meta director. You see that here as well. I showed you this one. And then you can also take a meta director, convert it into an ortho para. And then with an acyl group, it's meta directing. Then if you do a Clemmensen reduction, you convert it into an ortho para. Now, I don't ever think about things. I don't try to memorize this table whatsoever. Okay, I just try to think, what's the best strategy, and if I need to put these groups in this order, what would I put first? But there are a lot of judgment calls when you're doing some of these syntheses, so that's actually kind of rewarding, when you can figure them out. So let's see here. It says here, additional consideration is required when one of the groups requires more than one step to install. So remember, if you want to put in an amino group, first you have to do a nitration. So nitration, and then after that, you have to do a reduction. So you have the nitration, and then you have the reduction. So it's 2 steps. And so along the way, when you put the nitro group in, it's going to be a meta director. But then when you throw, or when you do the reduction, then all of a sudden you turn it into an ortho para director. So depending on where you want the chlorine, right, when would you put the chlorine in? You would put the chlorine in here before you do the reduction. Give me a thumbs up if that makes some sense. Right, you would not put the chlorine in at the end, right? You'd have to do it somewhere in here, in between, after you form the nitro, but before you reduce it. Good. So the order of operations is very, very important in these reactions. Extremely important, I should say. And so here, first, what you would do is the nitration, then you would do the chlorination, right? Because you would have your intermediate after the first step would be nitrobenzene, right? And that's going to direct you to put the chlorine here, right? Then you can do the Clemmensen, just the zinc reduction, and then you wash it with sodium hydroxide to convert the aniline ion to the free base. So there you go. So again, order is very, very important in these. And so before we can get into more synthesis strategies, this is one of those parts of the class it's not tough to teach it, but it can be frustrating for students at this point. So let's take a deep breath, okay? Okay, let's take a deep breath and realize we have covered a lot of material, okay? Trust me, this guy knows, okay? We covered all of this in gross and gory detail. And then we also covered the table with all the ortho para directors, meta directors, strong, weak, moderate activators, and deactivators. So now we're going to take all that information, and the next part here deals with a couple other limitations. Okay, these are limitations, They're covered in any organic chemistry textbook, my friends. So trust me, it's not just a David Klein thing. It's something that's important for all organic chemists. Okay, so I'll just walk through them with you, and then I'll try to point them out whenever they come up. So the first one is nitration. Okay, you can't do a nitration on a ring when it has an amino group on it. Now, why wouldn't you be able to do that? Well, the reason why is, first of all, if you, sorry, where's my black pen? If you were to treat this, with nitric acid and sulfuric acid, it says here it can be oxidized with HNO3 and H2SO4. Well, first of all, you're going to form the aniline ion, right? Which has a positive charge on it already. And this is going to be so strongly deactivating that it's going to cause the ring to be unreactive at all, okay? So that doesn't work. So if you have aniline or some kind of aniline derivative, and then you try to do a nitration, it just doesn't work, okay? It doesn't work whatsoever. All right, the next thing is Friedel-Crafts turns out is actually kind of a sensitive reaction. It only works when the ring is moderately deactivated, or when it's activated. If it's moderately or strongly deactivated, so if you have some kind of moderate deactivator or a nitro group which is strongly deactivating, Friedel-Crafts doesn't work, okay? It will work with a weak deactivator. Sure, it'll work with a halogen, it'll work with a weak activator, moderate activator, but if you have something that's moderately or pretty deactivating, Friedel-Crafts just doesn't work, okay? So Friedel-Crafts is a bust in that case, all right? So with those two limitations in mind, okay, you got to remember these. And are they difficult to remember? Sometimes they can be. But I've taught the class long enough to know that we don't set our students up with an abundance of problems where these show up. They can show up. It's not that it's unimportant, but it's not like they're going to rear their head in every stinking problem that you see, okay? But just kind of be cognizant of these two concepts, okay? So with that in mind, let's see. I didn't give myself a lot of room here, did I? No, it says you're starting with benzene. So I might need to switch over to a blank document for this one, but it says starting with benzene and any other reagents of your choice, come up with a synthesis for each of the following compounds. Some of the problems have more than one plausible answer. Okay. So we'll start with the first one. So you'd call this orthobromoaniline, this compound here. So we have the amino group, which has a lone pair on the nitrogen, so it's an ortho para director. And then we have the bromine, right, which is moderately deactivating, but it's also an ortho para director. However, you know that the amino group came from, right, the amine, that came from, this is a retrosynthesis here, you know it came from a nitro, because we're going to have to put a nitro in, and then we're going to have to reduce it. So based off of that, which one of these groups would I want to put in first? Would I want to put in the bromine or the amino or the nitro group? And it's not a trick question. Does anybody have an idea? So I couldn't put in the nitro group first because the nitro is going to be a meta director, right? So that's going to be a meta director, and we want these two groups to be ortho to each other. So let me show you where I think we should start. I think we should start by taking benzene and brominating it, okay? So let's take benzene. Oops, let me use a thinner pen here. If we take benzene and we're going to brominate it. So we're going to treat it with some bromine and iron 3 bromide like this, and that's going to put the bromine, we'll just throw it here, okay? Now, that is an ortho para director, right? It's going to direct here, here, and here. But it's mostly going to direct to which position? Well, based off of sterics, it's mostly going to direct to the para position. So in order to get something in the ortho position, what kind of group am I going to have to use? Exactly, a blocking group. Thank you very, very much. Okay, so let's do that. So we'll put in some fuming sulfuric acid. So fuming H2SO4. All right. So, let's see here. So we'll put in our sulfonic acid. We'll do it like that. There we go. And so now the bromine is going to direct to the ortho position, and the sulfonic acid is going to direct to the meta position. So they're both directing to the same position. So now we can install our nitro group. So let's put in our nitro group. So we're going to do nitric acid and sulfuric acid, like that. And that is going to put, I didn't even give myself enough room. I'll put the nitro group here. My bromine is here. My sulfonic acid is here. So now I need to remove the sulfonic acid, and I need to reduce the nitro group. Boy, I'm really running out of space here. I'll just put dilute H2SO4. That will remove the blocking group. So that's going to put, that means I'm going to have my nitro and my bromine. They're going to be ortho to each other. And so now to get to the final product, I just have to reduce it. So you could use iron or zinc. I'll just put zinc and HCl. And then in step 2, I'll put sodium hydroxide. And that's going to change the, or convert the anilinium to the aniline. And so we're going to end up with our final product, which looks like this. So how many steps is that overall? Let's put 1, 2, 3, 4, 5, 6. So it's a total of 6 steps. This guy, it's quite a few steps to get this reaction to work. Anyhow, so for the next one, I'm going to switch to a blank document since I didn't give myself enough room here. So just bear with me for a second. And we're going to do 18.26b. So again, just bear with me here. There we go. So here's my blank document. Still get some space on here. So this is, what was it, 18.26b. So 18.26, and we're going to do B, which is going to be this compound. I'm going to make nitrobenzene. Just move this over here. There we go. So a nitrobenzene, and then we have a chlorine that's para 2. This synthesis isn't nearly as long as the first one. Which one of these groups should I put in first if I'm making this from benzene? Should I put in the chlorine first or the nitro group first? Anybody have a strong opinion about that? Remember, the nitro group is a meta director, and the chlorine is an ortho para director. Yeah, exactly. Exactly. Thanks, Erica. Perfect. So let's do that. We'll take our benzene. We'll put the nitro group in first. Cook it up in some nitric acid and sulfuric acid. Is that enough acid for you? I hope so. Dangerous. Got to be careful with that. Got to keep it on ice. Otherwise, it can get too warm. Okay, so now that we've got the nitro group, all we have to do is put the chlorine in. Now, the conditions that were listed on our slide were chlorine and aluminum chloride. Those are really great conditions. Aluminum chloride is a really excellent Lewis acid. So there we go. So we've got our nitro group and our chlorine. Hot dog. There we go. All right, that one not nearly as bad. Only 2 steps. 2 steps for this one. There we go. So not nearly as bad. And then the last one, C. So let me just scooch down here a bit. So this is 18.26C. We've got an amino group. Okay, and then we've got a butyl. I think it's a butyl, right? Is it a butyl group on there? No, it's a propyl group. All right, so we've got a propyl group on there. Now the propyl group, we know we have to put that on there by Friedel-Crafts acylation. So we know we've got to do Friedel-Crafts acylation with this, and then we'll have to do, because we don't want to get the isopropyl on there as well. So we're going to need to do Friedel-Crafts acylation there. And for the amino group, we know the only way to put that on is by nitration and then reduction. So what I would say, though, is, in terms of which one of these we should put on first, well, remember, an amino group is going to be a strong activator. Strong activator. Okay, so if that one's a strong activator, and then the acyl group is going to be a deactivator, and then the alkyl group is just a weak activator, I would put the amino group on first because it's going to give you a higher yield in the end. Okay, so let's put the amino group on, and then we'll do the Friedel-Crafts acylation, and then we can just do the reduction, and we're done. If you're wondering, could I do the acylation first and then the reduction? I would say, yeah, you could do either way. I would accept either one, and I didn't look at the solutions manual, so I'm not sure what he has in there, but I would say that either one of them is totally fine. So I'm going to do the nitration first, reduce it, and then I'll do the Friedel-Crafts, and then we'll do the Clemmensen reaction. So we'll take our benzene, we'll nitrate it the same old way. So a lot of the reactions in here are repetition. So a lot of it's the same old stuff. It's almost like the alkenes chapter where it's like hydroboration, oxidation a million times over. So this chapter is kind of like nitration a million times over. So we put in our nitro group, and then we reduce it. I'll use zinc and HCl this time. Sometimes I don't put the heat in. I think in the textbook he puts heat. It's not always required to heat these up, but anyhow, I'll put heat. It's probably more correct. So we have our amino group. Now we can do our acylation. I just lose everything. Yep, I did. Okay, so let me start over. So this is 18.26 C. So we start out with benzene. We're going to do our nitration. Sorry about that. We're going to make nitrobenzene. Same way we always do. We go. Then we're going to reduce it. We're going to use zinc and HCl, and we'll heat that up, and that's going to make aniline. So we have our amino group. Now we're going to do the Friedel-Crafts acylation. This is called propionyl chloride. You don't have to know the name of it. We're going to talk about that in chapter 20. So that's going to give us our acyl group. So we'll put that in here like this. So 1, 2, 3 carbons, and then we do the Clemmensen reduction in the end. So Clemmensen reduction is going to be zinc and mercury. So this is our zinc mercury amalgam and HCl. However, that's going to give us the aniline ion in the end. So I would say step 1 would be this. And then after that, step 2 is going to be sodium hydroxide in the second step to deprotonate. And so after that, that will give us the amino group in the correct position. 1, 2, 3. There we go. So that covers all the questions in 18.26. So now, if we go back to the chapter slides, so all the way down here. Oh, Mr. Dion, where were you? Oh, well, here we go. No, we covered that already. Sorry, here we go. 18.28. These ones are a little more complicated because you got 3 groups on them now. But what I'd like to do is take another break and let you guys give these a try. So I want you to at least try the first one. Why don't we do just the first one, and we'll save the second one for next class. So I want you to see if you can take start with benzene, and see if you can get to this big product here. And then we'll save this one for, that's going to be June, isn't it? So we're going to save this one for, it'll be June 3rd. So 0.60324. So I'd like you to try that one. And then after that, we're going to look at a new kind of reaction, which is called the SNAR reaction. So again, you've learned SN1 and SN2, and we're going to talk about the SNAR. Sorry about that. Can I take